Hello students, we are going to look at class exercise 3 for reactions and stoichiometry. Without further ado, we are just going straight into the question. These are some of the data we are given. We were told that we have 25 cubic centimeters of 0.2 moles per dm cube of aqueous potassium permanganate, and then after that we were told that it requires 25 cubic centimeters of 0.5 moles per dm cube of sodium sulfite for complete reaction. If you do a quick calculation, you notice that the oxidation state for sulfur here is +4. Okay, so it's +4 over here. Then of course you know that manganese is +7. As what we often highlight in our tutorials and of course the lectures, that's the fundamental way of doing such redox questions is really to look at the electron transfer between the two parties. The simplest way is really, I think, number one, calculate the amount of permanganate you have first. Okay, so we're just going to jump straight into the calculation. So the amount of permanganate, MnO4 minus. Okay, so this will be equals to 0.025, that's 25 cubic centimeters, multiplied by 0.2. Okay, so we are going to get 5.00 times 10 to the power of -3 moles. Okay, so if you look at the data booklets, acidified potassium permanganate, upon fulfilling its oxidizing agent role, it will be reduced to Mn2+. So therefore it needs to take in 5 moles of electrons. So following up this calculation, we can calculate the number of moles of electron transferred. Okay, so this is a very important calculation. So we need to multiply this value by 5. Okay, so we're going to get 0.025 moles. Okay, then based on this, you will know that the electron transferred to 5.00 times 10 to the power -3 moles of permanganate, which is this amount, must come from this particular concentration and this particular volume of sodium sulfite. So again, we're going to calculate the number of moles of sodium sulfite. Okay, so therefore just going to punch the calculator right now. So number of moles of SO32 minus will be equals to 0.025 multiplied by 0.5, and then we are going to get 0.0125 moles. Okay, then from here we can conclude that 0.0125 moles of sulfites will give out 0.025 moles of electrons. So we can simply just take the ratio, okay, between sulfites and the number of moles of electrons. So this will be 0.0125 is to 0.0250, and then we're going to get 1:2. So for every 1 mole of sulfites, it gives out 2 moles of electrons. So because of that, its oxidation state will increase by 2. So therefore the final oxidation state of sulfur will be +6. So D will be the answer. Right. Okay, then we're going to move on to question 2. I think it requires a similar calculation. So I have a saturated solution of xenon difluoride. So the MR is given to be 169 in water, and then it contains 25.0 grams per dm cube of xenon difluoride. Okay, so you are given the concentration in terms of grams per dm cube. So maybe the simplest way is probably to convert to moles per dm cube. That will help us in our calculation. So we'll just take 25 divided by 169. Okay, if you wish to, you can just write out the numbers. If not, you can leave it for the calculation later. So I'm going to end up with 0.1479 moles per dm cube. Okay, and then the solution is a strong oxidizing agent. It will quantitatively oxidize another solution containing a certain concentration of chromium-3. So that's 0.150 moles per dm cube. And then you were told that xenon difluoride is reduced to xenon in the course of the reaction. Okay, then in the experiment, I used or rather they used 15.20 cubic centimeters of xenon difluoride. Yeah, so based on this, I'm going to calculate the number of moles of xenon difluoride here. Okay, so I can just perform a simple calculation. So that will be 0.0152 multiplied by 25.0 divided by 169. Okay, so I'm going to end up with, let me just punch the calculator, multiply by 0.0152. I'm going to end up with 2.249. Okay, so I'm just going to write it out. 2.249 times 10 to the power of minus 3 moles. Okay, and you were told that xenon difluoride is reduced to xenon, so therefore the number of moles of electron transferred, okay, in this case are taken in by xenon difluoride. Okay, so that will be 2.249 times 10 to the power minus 3 multiplied by 2. Yep, so again I'm going to punch my calculators, and then I'm going to get 4.497. Okay, so 4.497 times 10 to the power of minus 3 moles. Okay, and then you are given the volume of chromium 3, so this is 10 cubic centimeters, and you know the concentration is 0.150. So from here we can easily calculate the number of moles of chromium 3 plus. Okay, so that will be 0.010 multiplied by 0.150, and then this will give us 1.50 times 10 to the power of minus 3 moles. Yep, so same logic. 1.50 times 10 to the power minus 3 moles of chromium 3 will give out 4.497 times 10 to the power minus 3 moles of electrons to 2.249 times 10 to the power minus 3 moles of xenon difluoride. Okay, so that is the logic of doing such fundamental calculation, because you go back to the basic to determine the number of moles of electron transfer. Yep, then from here I'm going to do the same thing. I'm going to take the stoichiometric ratio. Chromium 3 is to number of moles of electrons, so that will be 1.50 times 10 to the power of minus 3 is to 4.497 times 10 to the power of minus 3. I'm going to get a ratio 1:3. So 1 mole of chromium 3 will give out 3 moles of electrons. So therefore, the oxidation state of chromium should increase from +3. Okay, so our case +3, because originally it's +3, then the final oxidation state will be +6. So it will be 3 units higher than +3. Okay, yeah, so the logic to do stoichio is very simple if you go back to the fundamentals. Right, okay. Then for question 3, we have an interesting compound known as hydroxylamine. So this compound contains both a hydroxyl group, that is OH, and the amino group, that's NH2. Yeah, quite a number of students misinterprets hydroxylamine to be a source of OH minus. This is incorrect. Okay, hydroxylamine is actually a covalent compound. Okay, contains NH2, and then the nitrogen is bonded to a OH. Yep, so it doesn't ionize to give you OH minus and NH2 plus. Yeah, so please do not have this particular misconception. I mean, if you do have, just make sure that OH, the source of OH minus is usually from solid group 1 or group 2 hydroxides. Yeah, then for the rest of the bases, they are likely to ionize in water to give a very small amount of OH minus, but you're going to learn more about it under the topic of acid-base equilibrium in JC2. Yeah, that will be 2024. Yeah, so at this stage, perhaps do not rush into it. Okay, you were told that it can be oxidized under acidic condition to give you either nitrogen, oxidation state 0, or nitrogen monoxide. That is N2O. So in our case for nitrogen monoxide, the oxidation state of nitrogen is +1. You might want to determine the oxidation state of nitrogen in the case of hydroxylamine. Yeah, so you can easily calculate it based on what you learned in secondary school. So you let it be X, so there are 3 hydrogens, so +3. And then you have oxygen, which is -2, equals to 0. So the oxidation state of nitrogen is -1. Okay, then with the aid of half equation, determine the number of moles of electron transfer per mole of hydroxylamine. Okay, so this is very important, huh? Per mole of hydroxylamine. Yeah. So in our case here, if the product is nitrogen, so I'm going to write it as NH2OH. Yeah, so again, oxidation state is -1. Okay, I'm just going to draw an arrow here, leaves a bit of space, and then I'm going to put half N2. Okay, so the oxidation state increases from -1 to 0 over here. So therefore, I'm going to give out 1 electron, so plus electrons over here. And then I'm going to balance the redox equations. Yeah, so the overall charge on the left is 0, on the right is -1. Okay, so in our case here, I'm going to perhaps add a H plus. Okay, I'm going to add a H plus over here to balance off the charge. And then after that, we need to balance the water. Okay, so balance O and H using water. So the total number of H on the left is 3, O is 1, on the right H is 1, no O. Okay, so I just need to add 1 water molecule to balance off the O and the H. Okay, yeah, so number of moles of electron transferred per mole of hydroxylamine is 1 in this case, so we give out 1 electrons. Okay, then we're going to do the same thing for N2O, so NH2OH. Okay, so this is -1. I'm going to draw an arrow over here, and then after that I'll end up with N2O, so I'll just write it as half N2O. Yeah, that will make our life easier. So half N2O here, and then this 0. Okay, sorry, this is not 0. I think earlier on I calculated to be +1. Okay, so this is +1. Okay, so 2 electrons is being transferred out. Okay, so 2 electrons, and then to balance the charge, I have to add 2H plus over here. Okay, and then I need to balance the rest with water. So 3H on the left, 2H on the right, so half H2, okay, that will give me 1H, and then half O, because half O plus half O equals to 1 O on the left. Yeah, so that should be it. So the number of moles of electron transferred per mole of hydroxylamine is 2 in this case. Okay, so with these half equations, it's going to aid us to do part B. Then for part B, it was found that the sorry, I need to change to this. Yeah, it was found that I have 80 cubic centimeters of 0.05 moles per dm cube of hydroxylamine. So in this case, let me calculate the number of moles of hydroxylamine and H2OH. Okay, so this will be 0.080 multiplied by 0.05. So I'm going to end up with 0.004. Okay, 0.08 multiplied by 0.05. So maybe I should write it in standard form. So that would be 4.00 times 10 to the power of -3 moles. Okay, and then I require 20 cubic centimeters of 0.4 moles per dm cube of iron 3, and then we were told that iron 3 is reduced to iron 2. So the number of moles of iron 3 plus is equals to 0.020 multiplied by 0.40. So that would be 0.4 multiplied by 0.02, that will be 8.00 times 10 to the power of -3 moles. Okay, in the course of being reduced from iron 3 to iron 2, the number of moles of electron transferred is therefore 1 per mole of iron 3. So total number of moles of electron transfer is 8.00 times 10 to the power of -3 moles. Okay, then we use the same logic as what we used earlier on, because this number of moles of electron transferred must come from hydroxylamine. So we are going to take the ratio between hydroxylamine and the number of moles of electrons. So that will be 4.00 times 10 to the power of -3 is to 8.00 times 10 to the power of -3. And then we are going to look at a ratio of 1:2. Okay, so therefore for every 1 mole of hydroxylamine, 2 moles of electrons is being transferred. Yeah, so based on the above, I'm going to pick the products to be dinitrogen monoxide. Okay, so that will be N2O. Yep, and I'm going to write the balance equation based on this. So NH2OH. So I'm going to have 2 iron. So 2 2Fe3 plus, okay, plus NH2OH, okay, I'm going to get 2 iron 2 plus half N2O, okay, half N2O, then plus 2H plus half H2O. Yep, so this will be the overall balance equation. Okay, so I hope you found the debrief or the review to all the 3 class exercises useful. We're going to go into energetics in the next chapter.